Good day everyone, welcome back to our chemistry series. Today we will be discussing further on isotopes. Isotopes. Isotopy is the phenomenon whereby atoms of an element exhibit different mass numbers but have the same atomic number. Thus, isotopes of an element have different physical properties but exhibit the same chemical properties. This is due to differences in the number of neutrons present in these atoms. Such atoms are known as isotopes. Hence, isotopes are atoms of the same element with the same atomic number but different mass number. The gigamolar counter is used to determine the different isotopes present in an element. Atomic mass unit. Now, an atomic mass unit with the symbol AMU or U, also called a datum with the symbol Da, is a standard unit of mass used to express the weight of atoms, molecules, and subatomic particles. It is defined at exactly 1/12 of the mass of an unbound neutral carbon-12 atom in its ground state. Now, what is a relative atomic mass? Now, the relative atomic mass of an element is the number of times the average mass of one atom of the element is heavier than 1/12 of the mass of one atom of carbon-12. The relative atomic mass of isotopes, molecules, and compounds can be measured using the mass spectrometer. Calculating relative atomic mass. Most elements in nature exist as a mixture of different isotopes because these isotopes occur in fixed proportions (abundances). The value listed on your periodic table is not a simple average but a weighted average that accounts for how common each isotope is in nature. Now, formula for calculating relative atomic mass. Now, the formula for calculating relative atomic mass is equals to the sum of isotopes mass times isotopes percentage divided by 100. Now, when isotopes are given as ratio, example 3:1, rather than percentages, the method is identical but you divide by the sum of the ratio parts instead of dividing by 100. Now, we have an example. It states that naturally occurring chlorine consists of two main isotopes, 35 with an abundance of 75.78% and 37 with an abundance of 24.22%. Calculate the relative atomic mass of fluorine to 2 decimal place. Now, our isotope 1 has the mass number of 35 and abundance of 75.78, and isotope 2 has the mass number of 37 and abundance of 24.22. Now, for our formula, we know that our relative atomic mass will be equals to the product of the mass and their abundances plus the product of the mass and the abundance of each of the isotope divided by 100. So our relative atomic mass in this case will be equals to 35 times 75.78 in bracket plus 37 times 24.22 in bracket divided by 100, which will be equals to 2652.3 plus 896.14 divided by 100. Adding our numerator, it will be equals to 3548.44 divided by 100, which is equals to 35.5 to 2 decimal place. We have another example from UM 2001. It states that an element with relative atomic mass 16.2 contains two isotopes S16-8 with relative abundance of 90% and SM8 with relative abundance of 10%. What is the value of M? Now, for our solution, our relative atomic mass will be equals to 16 times 90 over 100 in bracket plus mu times 10 over 100 in bracket, which will be equals to 16.2 since we were given the relative atomic mass. Simplifying both brackets, it becomes 14.4 plus 0.1 m is equals to 16.2, and collecting like terms, 0.1 m will be equals to 16.2 minus 14.4, which will make 0.1 m to be equals to 1.8. Now, dividing both sides by 0.1, it becomes 0.1 m divided by 0.1 will be equals to 1.8 divided by 0.1, which will make m to be equals to 18. We also have another example from 2009. It states that if 100 atoms of element S contain 70 atoms of S9 and 30 atoms of S11, calculate the relative atomic mass of S. Now for our solution, we know that our relative atomic mass will simply be the product of our isotope mass times their borders divided by 100 and adding it for each of the isotopes. So our relative atomic mass will be equals to 70 times 9 divided by 100 in bracket plus 30 times 11 divided by 100 in bracket. When multiplied, it will be equals to 9.6. So S has a relative atomic mass of 9.6. We have another question from 1991, and it states that which of the following is suitable for determining different isotopes present in an element which exhibits isotopy? A. Sensitive weighing balance. B. Cathode ray tube. C. Mass spectrometer. D. Gigamolar counter. And E. Iodometer. Now the solution is the gigamolar counter is used to determine the different isotopes present in an element, and the correct option is D. Our final question is from 2008, and it states that the mass spectrometer can be used to measure the mass of A, an atom, B, an electron, C, a proton, D, a neutron. Now solution, the correct option is A, to measure the mass of an atom. Here are some exercises for you to try your hands on at home. And for more insight on this topic, you can check out our chemistry textbook. You can get the hard copy in bookshops, or if you are interested in the soft copy, you can get it at the website on the bottom of the screen. Thank you.